Welcome to class today. I hope you're finding that everything's going well during this first week. And if you have any questions, I definitely want to encourage you to reach out to me by email. If we need to set up a Zoom meeting during office hours, we can do that. But I really want you to be getting off to a good start. So just keep in mind that you need to be watching each day's lecture videos, and be sure that you're also completing the homework that goes with that in WebAssign. If you have questions, another option is to join our Zoom sessions at 8 o'clock a.m. on Tuesday and Thursday mornings to get some help with some of the work as well. So just be sure you're keeping up with all that. And in today's video, we're going to be looking at section 1.2, part 2, which is the part on radicals. Radicals are very important as far as being able to progress in calculus and some of the other higher level maths. You really need to be able to simplify radicals, and so that's what we'll be looking at today. Okay, so when we look at the radicals, we know that this is the square root, and so I just want to kind of reiterate, and hopefully you remember this. When you have the radical here, and there's no index, this would be your index that's going to be located here. If there's no index that's written, then that's indicating it's the square root. If it happened to have a 3 there, then that's going to be like the cube root. A 4 written there would be the fourth root. So that is just indicating which radical we're working with. So when we look at being able to translate these, if we've got the square root of a is equal to b, then basically what that's telling us is that b squared is equal to a. Okay, and we get that just by basically squaring both sides here. Okay, so when we're talking about these and we're taking the square root, we need to know that a is positive. We're not able to take the square root of a negative number. And so just to kind of give you just to demonstrate this with some numbers, the square root of 9 we know is 3, and we know that because 3 times 3 is 9, and we also know that it's going to have to be greater than 0 to be able to take that square root. So that's just kind of some background information. Okay, so if we talk about the principles, the principal nth root of a is defined as the nth root of a equals b, meaning that b to the nth equals a. Okay, so that's the definition of it. And if n is even, then we have to know that a and b are going to be greater than or equal to 0. So if this is an even index, then we need to be sure that we're taking the square root. We can't take the square root of a negative number with that. Okay, here's some examples. I want us to practice writing these as writing the radical expression using exponents. So I always think of this as you've got your base, and you're going to have that to your power over your index. Okay, so this is your index, and this is going to be the power that I'm referring to. So when I go to write this using exponents, I'm going to have my base of x, my power is 3, and my index is 5. So if I were to translate this into an exponent, it would be x to the 3 over 5 to the 3/5. This one we're going to have a base of y, power of 3, and an index of 4. So it would be y to the 3/4. This one has an understood index of 2. So this is going to be x to the 5/2. This we would really need to rewrite. If you remember, this would be the square root of 3 to the negative 1 power, right? Because it's in the denominator here. So if we have just the square root, then we're going to have 3 to the 1/2. That's going to be raised to the negative 1. So we're going to end up with 3 to the negative 1/2 power. Okay, and we get that because it's in the denominator here. Okay, so some of our properties, if we're taking the nth root of the product of two numbers, we can split that up into two separate radicals with the same index here. Sometimes that's helpful in taking the square root or the cube root, because we can split it up so that we have a perfect square or a perfect cube, and it just makes it easier to simplify. And that's an example here. If we have negative 8 times 27, and we're taking the cube root of that, if we split this into 2, then the cube root of negative 8, if you look at 8 and do the prime factorization for that. 8 is 2 to the third power. So basically we're taking the cube root of negative 2 to the third power. When I have an index like this, it basically tells me how many I need to have in a group in order to take it out. So I have 3 and I need 3 to be able to take it out. So all of them are going to come out, and when they come out, it's going to come out as a negative 2, and that's where we get this negative 2 from here. If I look at the cube root of 27, 27, if I do its prime factorization, then I'm going to see that 27 is 3 to the third power. So if I'm doing the cube root of 3 to the third power, I have enough to form one group and take it out, and that's where I get this 3. So negative 2 times 3 is going to give me negative 6. If I look at one where I have division underneath the radical, it's very similar property in that we can distribute that index to both the numerator and the denominator. If we look at the fourth root of 16 and go through its prime factorization, then we'll see that the fourth root of 16 is 2 and the fourth root of 81 is 3 by the same process with the factorization. Okay, if you have two radicals that are one inside the other, then you're going to actually multiply these indexes together and to combine those. So you would have, if you had the square root of the cube root of 729, then that would be the same thing as this would be an understood 2. So 2 times 3 would give us 6 for the index there. Here, if I have the nth root of a to the nth, these are essentially going to cancel each other out and leave me with just the a. And that is in the case where n is an odd index. If n is an even index, then we need to make sure that this was positive, so it comes out as a positive. So we're going to have to put the absolute value around it. And that's really just a special case. It's easy to forget that, but it does need to be there. Okay. All right, so here's a few examples that I want us to look at. If we're going to take the cube root of x to the fourth, and I'm going to start with this with the very basics. And so if I have x to the fourth, and I have 4 x's, and I'm taking the cube root of that. So we said the index tells me what size group I need to form. So I need a group of size 3. So I'm going to look and see, here I have a group of size 3, and then I have this one that's left over. So this group is going to come out from underneath the radical. When it comes out from underneath the radical, I'm going to have just a single x. Okay, I'll still keep my cube root, and then I have this leftover x here. So it's going to simplify to be x on the cube root of x. Okay, if we look down here, I need to get the prime factorization of 81 before I can do anything. So if I break this down, I have 9 and 9. And once you do these a little bit, you'll remember them. So this is going to be, I have 3's and I have 4 of those. So it's going to be 3 to the fourth power. So this is the fourth root of 3 to the fourth, x to the 8th, y to the fourth. Okay, so on this one, I'm actually going to write it out again. I don't really encourage you to do that on each of these because once you understand the process, there's no need to do that. Okay, so I've got all of this written out here. I have an index of 4, so I need groups of size 4. So I have this group of size 4, have this group of size 4, this group, and then this group. Okay, so each of those are going to come out from underneath the radical. So I'm going to have the fourth root of, I'm going to have a 3 on the outside, I'll have an x, I'll have an x, and I'll have a y. So I get a 3 from this, an x from this, an x from this, and a y here. Have nothing left. So this radical is actually going to go away, and I'm going to be left with 3x squared y as my answer there. Okay, here's some other examples. But here we're starting to add radicals. So we need to do the prime factorizations for each of these and simplify it. So off to the side, somewhere you're going to need to do to find out what 32 is. And if we keep going here, you're going to see that it's going to be 2 to the 5th power. If I do 200, then let's do 100 times 2. This will be 10 and 10, 2 and 5, 2 and 5. So we end up with 2 to the 3rd times 5 to the 2nd. Okay, so if we're simplifying these, here we've got 2 to the 5th, and we're going to add to that 2 to the 3rd and 5 to the 2nd power. Okay, with this, these have an understood index of 2, so when it's not written, that's our size. So that tells me that if I've got 5 under here, I have enough for 2 groups. So I'm going to have 2 groups that come out, and I'm going to have a leftover 2. Here, I'm going to be able to take a 2 out and a 5, and I'm going to have a leftover 2. So I'm going to have 4 on the square root of 2 plus 10 on the square root of 2 is going to give me, because these are alike, I can combine them together. So it's just like adding like terms, and I'll have 14 on the square root of 2. Okay, on this one, I'm going to let you on your own do the prime factorizations of this, but this one is going to be 2 to the 4th times 3, and this one's going to be 5 to the 2nd times 3. Okay, so what we can do is here we can take 2 2's out. So if I take 2 2's out, I'll have a square root of 3 left, and I'm going to take a 5 out, and I'll have a square root of 3 left. So I'm going to have 4 on the square root of 3 plus 5 on the square root of 3 is going to give me 9 on the square root of 3 for my answer. Right down here, we need to go through and do the prime factorizations for each one of these. So this one is 2 to the 3rd. This one is going to be 2 to the 2nd times 3. This one's going to be 3 times 5. And this one's going to be 3 squared times 2. So here I can take a 2 out. I'll have 2 on the square root of 3. Here I can take a 2 out, and I'll have a 3 left in. So I'll have, sorry, this should be 2 on the square root of 2. Okay. 2 on the square root of 2. This one will be 2 on the square root of 3. This one, I can't do anything with that, so it's going to stay as it is. And then this one, I'm going to take the 3 out, and I'll be left with a 2 on the inside. So when I go back and look at this, this was a 2. Anything that's like, I can combine together. So this one and this one can be combined together. I'll have 5 on the square root of 2 plus 2 on the square root of 3 plus the square root of 15. And that's all I can do with that because I don't have any like radicals to combine together. Okay, if I look at this one, it says assume b is greater than 0. That's just basically a technicality to be able to go ahead and do the problem. So this is going to be 5 squared b, and then here we're going to have the square root of b to the 3rd. So I can take a 5 out, and it'll leave me with the square root of b, and I can take a b out, and it'll leave me with the square root of b. So one additional way to do this would be to factor out the square root of b as a greatest common factor, and then it would leave me with 5 minus b as my answer. Okay, here are a few that I would like for you to take some time to practice on your own. So if you will, just pause the video and practice these, and then you'll be able to check your work. Okay, here are the answers that you should have gotten for this. Do your prime factorizations. You'll see that you end up with like radicals that you can combine together. Same thing with this one, simplify, and then you end up with some like radicals. At this point, you can go in and look for your greatest common factor, which is the square root of x. And when you take that out, you're left with the 4 plus x squared. This one, you've got groups of size 3. Be sure that you do write the index on your answer. It is important to continue to keep that same index throughout the problem. So here we'd have x squared, y squared on the cube root of y squared, z squared. And the last one here, very similar to this one, except this does have an even index. So when you pull a variable out from underneath an even index, you need to put the absolute values around it. With the C here, we don't really have to do that because we're squaring it anyway, so this would be a positive quantity regardless. Okay, here we have another example. This is one that it's going to be easier to go ahead and factor underneath the radical. So we see that we have a greatest common factor of 49 that's common to both. So we'll have x squared plus 1. And this is one that we can use some of our properties and split it up. We'd have the square root of 49 and the square root of x squared plus 1. And hopefully you recognize that the square root of 49 is 7 because that's a perfect square. And we're left with 7 on the square root of x squared plus 1. Okay, I want to talk for just a minute about multiplying radicals. The thing you need to remember with multiplying radicals is you either multiply what's outside the radicals together or you multiply what's inside the radicals together. You don't mix the two. So you're not going to multiply an outside to an inside or an inside to an outside. So if I'm looking at this, this has basically a 1 in front of it. So 5 times 1 is going to give me 5. And then the square root of 3 and the square root of 3, I'm going to multiply what's underneath those and I'll get the square root of 9. Hopefully you recognize that the square root of 9 is 3, and so we end up with 15 as our answer. Another way to think of that is the square root of 3 and the square root of 3. When you multiply two radicals together and they're both square roots, those are going to cancel and leave you with whatever was underneath there, which was the 3. Okay, if we look at this one, we'll multiply outside to outside, so we'll have negative 15. Then we'll do inside to inside, and we'll have the square root of 14. If we look at this 14 and do its prime factorization, it doesn't break down any more than 2 and 7, so this can't be simplified. If it could be simplified, like if this were a 12 and there was something we could take out once we did its prime factorization, then it would not be completely simplified until you do that. So just be sure that you are completely simplifying your radicals. If we look at this problem here, we want to distribute through. So we'd have the square root of 2 times 3. We have something under the radical and something that's outside. So we're going to just keep it in that same way. The 3 stays outside and the 2 stays inside. And then on this one, we've got a radical times a radical times 5 will give us 10. And there's nothing we can break out to get that simplified any further, so that would finish it up for us. Okay, so a couple other properties of radicals that I want to mention. If you have one that's combined as a fraction here, what we can do is split that up, and this goes back to some of those first properties we looked at. So we can simplify this. This is going to be 3 to the third, and this is going to be 2 to the fourth. Okay, so here we would have 3 on the square root of 3, and here we will have 4. Okay, because we know that the square root of 16 is 4. So at some point, if you recognize it, go ahead and put that in. If you don't, then you can see you take 2 2's out and you get 4. So that would be our answer. If we could reduce this, it would have to be the 4 would have to go into the 3 for reducing. We would never do the 4 out that's outside with the 3 that's inside to reduce. Okay, here's one. If we go with the cube root of 3 over the cube root of 8, the cube root of 3, we can't do anything with that, so it's going to stay as it is. And the cube root of 8 is actually 2 because 8 is 2 to the third power. So this would be our final answer. This one, if we multiply these two together, I'm going to have the square root of x to the third, because if I'm multiplying what's underneath here and x times x squared, we add our exponents and get x to the third. Anytime the power is higher than the index, then I need to take something out. So I can take out an x. I'll be left with x on the square root of x. All right, so if we want to write these as rational exponents, we've already practiced this a little bit, but we'll look at it again. Here we'll have x to the 3/7. This is going to be 5. If we have a square root, that's the same as 5 to the 1/2. So this is going to be 5 to the negative 1/2 power, so it's in the denominator, because this will be like an understood 1, and this is going to be an understood 2. Okay, if we look over here, this would be y to the 5/6, and this would be y to the 7/13. thirds. Okay, so if we want to combine these together, which we should because they are actually like bases, then if we're multiplying those together, that means we're going to add our exponents, so 5/6 and 7/3. This is where you would need to get a common denominator. So if we've got 5/6 and 7/3, our common denominator would be 6. So we're going to multiply both of these by 2. So we'll have 5 plus 14 over 6. So 19/6. So this will be the same thing as y to the 19/6. Okay, we've been working with radicals and converting those to rational exponents if we needed to and so forth, but sometimes it's just helpful to be able to work with these rational exponents as well. So if we're combining on one like this where we have like bases and we're multiplying those together, then that means we would just simply add our exponents. If we're adding our exponents, 1/3 plus 7/3 gives us 8/3. So we're going to have, this would be a, so we're going to have a to the 8/3. Okay, on one like this, we've got to combine these together. So we're going to have a to the, add these exponents together. So that's going to be 9/5 over a to the 3/5. If you remember, when we're dividing like bases, we subtract our exponents. So we're going to have a to the 9/5 minus 3/5. So we'll have a to the 6/5. Okay, and then down here, if you have this exponent outside, just like if it were a 2 or a 3, we're going to do it the same way. So we're going to have 2 to the 3/2, a to the 3 times 3/2, and then b to the 4 times 3/2. So we're really not able to do a whole lot with this. We'll have 2 to the 3/2. This is going to be a to the 9/2. And then this is going to be b to the 12/2, which would be 6. Okay, we can simplify this just a little bit because typically, if especially a number like this, this would be the same thing as the square root of 2 to the 3rd. So we'll have 2 on the square root of 2 times a to the 9/2, b to the 6th. So sometimes you just really have to listen to your directions and see at what point you need to stop. And so either this step or even this step would really be acceptable. Okay, so here's some to practice writing with rational exponents. This one we've got the x to the cube root of x to the 4th is in the denominator. This would be the same thing as x to the 4/3 if we were to write that, and because it's in the denominator, it would be x to the negative 4/3 if we're writing it as a rational exponent. Remember, rational means fraction, so you're going to be writing these so that you have a fraction in your exponent. Okay, this is going to be 2x to the 1/2 times 3x to the 1/3. Okay, so the 2 and the 3 will multiply together and give me 6x, and then we need to add our exponents. So if we have a half plus a third, then our common denominator would be 6. So multiply this one by 3, this one by 2. We're going to have 3 plus 2 over 6, or 5/6. And again, you've got your calculator. You can can do some of this in your calculator if you need to. So this would simplify to be 6x to the 5/6. This one here, this is going to be the square root of x to the 1/3. So I would suggest taking this part and rewriting it first as x to the 1/3. And then you're going to have x to the 1/3 raised to the 1/2 power. We're multiplying here, so we're going to have x to the 1/6. Okay, so one of the last things I want to talk to you about is rationalizing the denominator. In math, we typically do not like to leave radicals in the denominator, so anytime we have a radical in the denominator, we want to try to get rid of that. We're going to do that by, in most cases, multiplying by the square root. If it is a square root, you're going to multiply by the square root the identical square root, and then they're going to cancel. It's a little different if it's cube roots, fourth roots, and so forth. We'll talk about those here in some examples. Okay, so if we look at this first one here, we've got 2 over the square root of 3. It's a square root, so I'm just going to go in and multiply by the square root of 3 over the square root of 3. This is equivalent to 1, but anything over itself is 1, so I'm not changing the value of it, I'm just changing the form of it. So here, when I multiply, I'm going to get 2 on the square root of 3. This is going to give me the square root of 9, and we know that the square root of 9 is 3. Okay, so that would simplify that one. This one's a little bit tricky in that we have to actually think about what is it going to take to create a perfect cube underneath the radical. So we have one base of 5 here, but in order to create enough that we could get rid of the radical, I'm actually going to need a total of 3 5s. So I have 1 5. I'm going to put 2 more here, and again do the same thing to the numerator so that I'm not changing the overall value of it. So I'm going to have the cube root of 5 to the second. Here I'm going to have the cube root of 5 to the third. Okay, so it's important that these match up. That's kind of the whole reason for choosing what I did here, is so that I had the 1, I put 2 more with it, ended up with a group of 3. So now this and this is all going to cancel. I'm going to have the cube root of 5 squared, and I'm just going to be left with 5 in the denominator. Okay, this one here will have the 7th root of 1 and then the 7th root of a to the second. Any root of 1 is just going to be 1. Okay, so with this one, I've got to figure out what I need to multiply it by. Okay, so I'm going to give myself just a little bit more room here. So I'm going to be multiplying it by the 7th root of something. I have to figure out what that something is. So I know I need a base of a, and I need to have a group of size 7. I have 2, so I need to put 5 more with it. So I'm going to have I'm going to have the 7th root of a to the 5th, and then I'm going to have the 7th root of a to the 7th. And again, the purpose of doing this is so that now these cancel. I'm just left with a in the denominator. Okay, here are a few for you to practice with. If you'll pause it and then check your answers, then that would be helpful. Okay, take your work with these problems and look and see what you should have done. If you still have questions after going through this video, then feel free to email me and we'll try to figure out what the problem is. Okay, I have 2 more slides of practice problems for you to try. If you feel comfortable with simplifying radicals, then it's not necessary to try these. If you're wanting more practice, then go through these and check your answers and make sure that you understand how to complete those. Okay, check your answers on this slide to make sure that you've done these correctly. Okay, take a minute and check over these if you work these out. One thing I will remind you of is, since these are even indexes on 13, 14, and 15, that when you take a variable out from underneath the radical, you do need to have absolute value marks around that. So these would be absolute value. This one we don't have to put it around x squared, because if we square anything, it's going to be positive. Here, same thing with the b and c, they're going to be positive regardless, but you do need it around this. We don't need absolute values on the odd indexes, so no need to put them there. Okay, so that takes us to the end of this on radicals. We looked at a lot of examples today. Hopefully you are comfortable with simplifying radicals, and people are at different places as we start this semester. So hope if you went through it quickly, then feel very comfortable and satisfied with that. And if you didn't, then go back and rewatch it and make sure that you're comfortable with being able to simplify radicals. Okay, have a good day.